So this video is on Gauss's law. Here it is in mathematical form. The electric flux, which remember that is a two-dimensional integral of the electric field dotted with the area element, and it's the electric flux through a closed surface. Remember that is a surface that surrounds a volume all the way around. This flux is equal to the charge that is enclosed by that surface, the charge that is in the volume over epsilon naught. And this is a tool that we'll often use to find the electric field when we don't know it already. And so let's see how that works for a case where we know the answer, and that's going to be a point charge. So for a point charge, that's going to be a setup like this. We've got our charge. Let's just make it positive for argument's sake. We know that the electric field of a point charge goes out radially like this. It gets weaker as you get farther away, stronger as you're closer in. So that's what the electric field's doing. We can pick any closed surface we want. Remember, we always got to pick the area that we're finding the flux through. But we need it to be a closed surface for this equation to be true. So let's go ahead and pick a sphere to be our volume, and then the area that we're using is going to be the surface area of a sphere, like this. So this guy, these areas that I pick, they're going to be the surface area of a sphere, and I'll just say it is a sphere with radius big R. Now we're going to set up this integral. Okay, so this side I can do. I can look at my green surface and say how much charge is inside of that. Well, just the point charge itself, so the enclosed charge is just plus Q. The epsilon naught, it's a constant, it just comes along for the ride like that, and now we have to deal with this integral over our green surface. So first thing is we got to figure out what this area element is. We're doing a sphere, that's going to be spherical coordinates. So what is dA on the surface of a sphere? All right, well, what are integration variables? You have to go around the sphere like this, and then we also have to go around the sphere like that. Going around like this, that is the variable we call theta. And it's going to go from 0 to pi. So that one goes 0 to pi. Halfway around, and then the variable that goes around the circle like that, around the front and around the back, that's phi. And because it's going all the way around the circle, it goes from 0 to 2 pi, full way around the circle. So those are integration limits. It's going to be theta, 0 to pi, and phi, 0 to 2 pi. And that means when we're figuring out our area element, we need a length in theta, and we need to multiply it by a length in phi, and this guy's a vector, so we need to know direction. Well, everywhere that is perpendicular to the surface coming out here, so over here it would point out like that, over here it would be pointing out like that, over here like that, over here like that. That's the radial unit vector, so the direction here is going to be r hat. Okay, now what is a length in theta? That's going to be an arc length. It'll be the radius times a little step in theta, but here, for our surface, the radius is always this big R, so we can go ahead and write that in. And then a length in phi, well, that is also going to be an arc length, but it's going to depend on theta, because how long this path around is different here than it is up here. And so it's going to be the radius times sine of theta, little step in phi. And again, r is still big R. Okay, so altogether, taking these three pieces of information into account, my area element is two of the r's, r squared, a sine theta, d theta, d phi, r hat, and that is my dA that goes in here. I'm going to try and write it backwards so I can fit it all in. All right, all of that is dA. E, we're pretending we don't know, so we're just going to leave it as E. And then the integration limits, those are going to be in theta 0 to pi, in phi 0 to 2 pi. And now we're ready to start trying to do this integral. But first, I'm going to clear this out so I have more space. All right, so we got this integral. First thing to do is try to simplify it by pulling everything that doesn't depend on theta or phi out of the integral. So big R hat doesn't, because everywhere you are on the surface, the distance from the origin, the center of the charge, is always big R. So R squared can come out. There we go. Okay, sine theta, no, that definitely depends on that. R hat, bummer, it actually does too. R hat points this way when you're here on the circle, but up there when you're there on the circle, so we can't even pull the unit vector out. That's no good. But what about the electric field? Well, we don't know, or we're pretending we don't know what the formula is, but maybe we can say, okay, for this charge, the electric field's always pointing out. So we can sort of guess something about what has to be true about the electric field. Namely this, the electric field, it's a vector, and it must point out radially. So we're not putting in the formula yet, but we are saying it's in the R hat direction. Okay, here's why that helps. Got our integration limits. I'm going to plug in what we know or what we've guessed about the electric field. E R hat. We still have that dot product. Well, the only things with distance that are going to react to the dot product will be this other unit vector over here. So I'm going to pull that one forward. There we go. There's the R hat from the surface. Oops, already got the R there. Now a unit vector dotted with itself is equal to 1, because it is obviously parallel to itself, and it's also a unit vector, so its magnitude is length 1. So this is going to become 1. Yay, even though it changes everywhere on the surface, it is always pointed in the same direction as the electric field. So that's taken care of. All right, so knowing this, we can just say, let's replace this with 1. And then, of course, anything times 1 is just the same stuff, so we don't have to write anything in there. Okay, what else can we do? Obviously, the sine theta can't come out of the integral because one of the integrals is with respect to theta. These guys can't. Those are the things times what the integration variables are. What about this guy? What about the electric field? Well, all right, so let's put in some more information there. The electric field depends on the distance from the charge. But for our green Gaussian surface, we're always the same distance from the charge. We're always this big R away from the charge. So on this green surface, the electric field is always going to be constant because it's always at a constant R. So we already put this bit of information in. Let's do this new bit of information. Namely, E is constant on this surface. If we admit that we know that, now we can pull E out of the integral. It doesn't depend on theta or phi. So we get R squared times E. They're both outside of the integral. They are constants with respect to this integral. Then we have an integral in phi, going from 0 to 2 pi. Now these two are theta, so the only thing that we have to do for the integral is the d phi, and that integral I actually know how to do. It is just going to be 2 pi minus 0 or 2 pi. Alright, that's the phi part of the integral. Next integral, theta from 0 to pi of sine of theta d theta. And then we'll finish off the equation. And this integral we actually also know how to do. The integral of sine theta with respect to theta is negative cosine. So this thing is going to become negative cosine of the upper limit, cosine of pi minus negative, so that becomes a positive, cosine of the lower limit, 0, and cosine of 0 is 1, and cosine of pi is negative 1, so negative cosine of pi is also 1. So this integral is actually 2. All right, so now let's solve for the electric field, which is what we wanted. We have 2 pi times 2, that's going to be 4 pi, so let's move that over to the other side. And then we have r squared over here, so let's move that over to the other side. And we're left with e. Okay, so that should look pretty familiar. 4 pi epsilon naught, the charge q, over r squared. But of course, the electric field is a vector, but we already admitted that we knew the electric field just went in the r hat direction. So the direction of this guy is r hat. Now the other thing to note here is we made up this green surface. It was totally our choice to figure out what closed surface we wanted to integrate over to get the flux. So we could have picked any r. We could have picked a little tiny r, had a really small little sphere around the circle. We could pick a huge r. So really, this is kind of a variable. We could have stretched or squished the surface however we wanted. So let's replace this guy with the normal little r that signifies this is variable. All right, so that is definitely the electric field of a point charge. Q over r squared r hat, and then the 1 over 4 pi epsilon naught, Coulomb's constant. So it worked for a point charge, but there were a couple of things we had to do to help it along. The first one is we had to know what direction the electric field was. We needed to know this so we could do this dot product right there. So that's one thing you need to know before you try to use Gauss's law to find the electric field. The next thing we had to know was that E was constant on the surface. So we needed to know what E was a function of. And we needed that so that we could pull this electric field out of the integral. So the two things we need to know are, 1, the direction of the electric field you're trying to find. You need to know that so you can do the dot product. The second thing is what E is a function of. So what this electric field depends on, which is which variables. So when you set up your Gaussian surface, or the surface, this closed surface you're going to do Gauss's law on, you can make sure that your integration variables are things that aren't going to have E changing. So here, we knew E only depends on the radius, so we picked a Gaussian surface that has a constant radius, because if the radius is constant, then the electric field is constant, and the electric field then comes out of the integral and makes the integral a whole lot easier to do. So if you can figure out these two things about your electric field, and you know what charge is causing that, then you can use Gauss's law to find the function or the formula for the electric field.